is Doppler's effect. Have you ever noticed that the sound of an ambulance siren changes as it passes by your scooty on the road? The siren sounds louder and more shrill as the ambulance approaches your scooty, but then changes its pitch as soon as the ambulance overtakes you. Each one of us has noticed this unique changing sound of the siren. This difference in the sound of the siren of ambulance or the horn of a scooty or a train is due to a scientific phenomenon known as the Doppler's effect. Like many other phenomena, Doppler's effect is named after a scientist, Christian Doppler, who is credited with its discovery. Doppler's effect is observed when the source of a particular set of waves is moving with respect to the observer. The frequency of the sound heard by the listener is not the same as the source frequency. The relative motion between the observer and the source causes increase or decrease in the apparent frequency. Let us try to understand different cases of Doppler's effect. Case 1. Stationary source and moving observer. When a stationary source produces sound waves of frequency f, then its wavelength in the air is given by the relation lambda not equal to v divided by f, where v is the velocity of sound. Now these waves are traveling towards an observer who is moving with a velocity v, not towards the source. Therefore, the relative velocity with which the sound of wavelength lambda naught will approach the observer will be v plus vo. Thus, the apparent frequency of sound heard by the observer, f dash equal to v plus v naught upon lambda naught. By substituting the value of lambda naught, we get f dash equal to v plus v naught upon v into f. Similarly, if the observer is moving away from the source with velocity v naught, then the relative velocity of sound will be equal to v minus v naught, and the apparent frequency heard by the observer, f dash, is equal to v minus v naught whole divided by v into f. Case 2. Moving source and stationary observer. When a source moving with velocity vs produces a sound wave of frequency f and the waves travel towards an observer with velocity v, then it has the wavelength lambda not equal to v divided by f. The relative speed of sound reaching the stationary observer is equal to v minus vs. Therefore, the apparent frequency of sound heard by the observer f dash is equal to f into v divided by v minus vs. Similarly, if source is receding away from observer, the relative speed of sound is equal to v plus vs, and the apparent frequency heard by the stationary observer f dash is equal to f into v divided by v plus vs. Case 3. Moving source and moving observer. In this case, if both the source and the observer are moving in same direction with velocity vs and v naught respectively, the sound wave produced by the source has frequency f and the apparent wavelength is equal to v plus vs whole divided by f, where v is the velocity of sound. Now this sound wave will approach the observer at relative velocity of v plus v naught. Therefore, the apparent frequency of sound heard by the observer f dash is equal to f into v plus v naught whole divided by v plus vs. Now, looking at the expression of apparent frequency given in this formula, we can easily develop a general relation for finding the apparent frequency heard by a moving observer due to a moving source, that is, f dash equal to f into v plus minus v naught whole divided by v plus minus vs, with the sign of car be determined using relative motion between the observer and source. Let's understand a shortcut trick for remembering the formula of apparent frequency. Whenever source moves towards the observer, then do subtraction in denominator, and if the source moves away from the observer, then use addition in the denominator. And whenever observer moves towards source, then do addition in numerator, and if observer moves away from the source, then do subtraction in the numerator. Let's solve an example to understand this concept better. Question. A train is moving on a straight track with speed 20 meters per second. It is blowing a whistle at the frequency of 1000 Hz. The percentage change in frequency heard by a person standing near the track as the train passes him is close to speed of sound is equal to 320 meters per second. The options are 12%, 6%, 18%, 24%. This question was asked in JEE Main 2015 exam. Solution. From the question, we can clearly identify that this is the case of a moving source, that is a train, and a stationary observer, which is a man. We are given the speed of train Vs equal to 20 meter per second and the speed of sound V is equal to 320 meter per second. The frequency of whistle F is equal to 1000 Hz. We have to find the percentage change in frequency heard by the observer as the train passes by. So the frequency heard by the observer while the train approaches him can be calculated using the relation F1 equal to F into V divided by V minus Vs. That is 1000 into 320 divided by 320 minus 20, which is equal to 1066.67 Hz. And the frequency heard by the observer while the train recedes, F2 is equal to F into V divided by V plus Vs. That is 1000 into 320 divided by 320 plus 20, which is equal to 941.18 Hz. Now the percentage change in frequency is equal to modulus of F1 minus F2 whole divided by F1 multiplied by 100, which comes out to be approximately 12%. Hence the correct answer is option A.